You have elevation differences. Again, the air starts to move when we have elevation differences. So either in the mountain ridges or along the coast, everywhere we're in good shape, or where we have large lakes, like water meadows. This is a picture of West Texas. West Texas has become the wind capital of the nation. Compliments of General Electric. One problem is that we don't live in West Texas. We all seem to live in South Central Texas. That's where the majority of Texas population resides. So there's a bottleneck right now into bringing all that energy to where it's needed. And that means building more distribution lines, and that is a long-term process. You have to acquire land from owners and, you know, negotiate right of way and do a lot of permitting. So we're talking about a process which takes many, many years to be completed. But we can be proud of the fact that we are the wind capital of the nation. Inside a wind generator, there's two things. A wind generation moves fairly slow. It goes like so. If it would go any faster, it would take off. A generator needs to go much faster, about 360 revolutions per minute. I'll save you why, just believe me. So we have to have a gearbox in order to make that speed increase from a few revolutions to a few hundred revolutions per minute. And that's why these things have this big chumby box on top of the pole. This is the first wind generator made out of wood. This is what you see when you drive down the freeway and you go on down to Big Bend or New Mexico, Amsterdam. These machines will power more than 1,000 homes. More than 1,000 homes. That's a lot of power. They are huge, as this picture illustrates. This is a gentleman standing on a crane platform doing some maintenance at the tip of a blade. It gives you a feeling of the proportion of these machines. This is a picture of one of these blades you've seen go down the freeway, which is, you know, right now about 200 feet. This is in meters. Industrial measurements are always metric. But we're looking at going to 300 meters. Okay. Today, our biggest machine is 5 megawatt, which, like I said, can power 2,000 homes. So it's a very efficient way of power distribution. That's what you will see when you travel. And like I explained to you, you want to make sure that you're about 50% above the highest point of obstruction to catch that free airflow. One of the reasons that a lot of wind farms are planned offshore is two reasons. To do away with the objections of the NIMBYs. It is an awkward, unsightly thing to have a 300-foot machine in your backyard, and it makes ziffy noise and all kind of objections. I will not speak about the bird problem because I don't want to offend anyone here. But offshore, we have none of these problems. We have no people, we have no NIMBYs, and we have lots of wind. And we know how to build offshore structures, and we know how to run submarine cables to bring the power back to shore. So why not? So many wind farms, for that reason, are being planned and built offshore. And like the gentleman in the back said, we have wind many times when we don't have sun. I'm going to give you some practical examples, a lot of it from the farm. This is on my list of things to do. Our house in the farm is currently being cooled with natural air conditioning. It's a compliment to Mother Nature. But as we get older, we tend to be less tolerant to extremes. And that is across the board, and that includes temperatures. So we're beginning to feel that in the deep of winter and in the height of summer, we're not as comfortable as we would like to be, as we are in the Silver Ages, in the Silver years. So this is an example of what we can do other than our normal run-of-the-mill Freon-based air conditioning systems, which almost all of you in this tent have, which is very energy inefficient. It is responsible for 3/4 of our power bill. And it basically, what it does, it compresses a gas to a liquid, in this case Freon, and when we then vaporize that gas in our air handler, it drops 20 degrees in temperature, and we blow that into our home, and we'll get the return back, and we'll keep on lowering that temperature. The problem is that compression has to be done by electricity, an electric pump, which takes an enormous amount of electricity, more than anything else you've ever dreamt of. And as I said, it's responsible for 70–80% of our power bill, which is a lot. So, as I mentioned before, one of the very important things in this whole arena of energy is we need to learn how to do better. We need to change the way we use energy. And there's better ways. This is an example of chilling, i.e. cooling, but we're using, first of all, a different medium. It is ammonia instead of Freon. And ammonia acts the same. It needs to be changed to liquid form, and then when you vaporize it, it drops 20 degrees in temperature and does the same trick. The only thing is, to make ammonia into a liquid, you simply heat it, which takes a lot less energy than compressing Freon with a big old compressor. So this actually uses natural gas or propane gas. It's kind of odd to make cold with heat, but that's what it is. And it compresses that, that gas to a fluid, and in the home we change it into a vapor. So I need to lubricate my throat. And what happens in the home is the following. The cold water, which is about 45 degrees, we actually use water to cool, in that unit which you just saw. And we run that in the home along the ceiling in copper pipes. This is a schematic of what happens here. These are the copper pipes. This is winter and summer. In the summer, the hot air rises, and it meets these copper pipes near the ceiling, which are cold. There's cooling fins on there. So what happens? The air lowers in temperature. And what happens with colder air? It falls. It drops. It drops right back into the room. So we have what's called natural air convection. We don't need an air handler, we don't need blowers, we don't need filters, we don't need registers. It's one of the simplest things you can think about when we talk about how can we cool and heat our spaces, because in the winter we can simply reverse the process and heat the water instead of cool. Most of the houses in colder countries are heated with hot water running through the rooms and radiators and pipes. So we simply do the same. We run the water again through the same copper pipes, and we heat the air, the cold air, and we start from the top down to fill up the room with warm air. And we're home free. And come Sunday, we flip the switch and we start chilling the water again. So you say, well, why don't we do this? I haven't never heard about this. Well, for many reasons. The biggest reason is that we have always had an abundance of cheap energy. We never had to worry about where does it come from, how much does it cost, how much do I need, because it was simply there. We were educated by the fact that all we have to do is flip the switch and it's there. Producers of electric equipment, appliances and engines never were told design with energy efficiency in mind, because there was no such thing. There was no incentive. Only now are we beginning to understand that this is an issue. So we're beginning to see energy efficient appliances. There is a Department of Energy program called Energy Star, which helps us as consumers to find and to rate these appliances. Each appliance has a little yellow card inside by law which says average annual energy consumption, so many kilowatts. And you'll be surprised if you go into a Conn's or a Home Depot or Lowe's or wherever you shop, and you take 10 equally looking refrigerators,